Okay, and for those of you impatiently trying to decide why we would want something that doesn't actually tell us molecular structure, after this video, we're going to pull these pieces together and figure out how to go into a molecular formula from empirical formula. But first, there's one more way to determine an empirical formula, and this one we're going to do if you have percent composition and you want to get to empirical formula from there. So recall the last time we went from mass to moles and then moles to our empirical formula. This one we have percentage of each, and we want to get into moles to get to our empirical formula. So you'll notice that the first thing I did was go to the periodic table and pull off the grams per mole for each atom in this compound. The next thing I want to do is make an assumption that might not seem too intuitive, but actually works quite beautifully. If we look at these percentages and treat this compound as being 100 grams total, then we can turn this into saying this compound has 68.8 grams of carbon, 5.01, I feel like I left something off there. Yeah, nope, just 5.0 grams of hydrogen and 26.2 grams of oxygen. That will let me go straight from these percentages into moles, and then we just do the last step where we divide by the smallest mole. So let's do that. So for carbon, I have 12.0, nope, so I caught myself. We're going to end up with the wrong units on top. Remember, we want moles on top. So we have 68.8 grams of carbon times 1 mole of carbon per 12.011 grams of carbon equals, and then hydrogen, make sure you can see good, I have 5.0 grams of hydrogen times 1 mole of hydrogen per 1.008 grams of hydrogen. And oxygen, I have 26.2 grams of oxygen times 1 mole of oxygen per 15.999 grams of oxygen. Let's check our units out. Cancels, beautiful. Beautiful. So now let's button push and see what we get. Then after some button pushing, I see that my smallest is going to be the moles of oxygen. So I'm going to divide everybody by the 1.639. So carbon is the 5.73 moles of carbon divided by 1.639. And hydrogen is 5.68 moles of hydrogen divided by the 1.639, and then oxygen is just 1. So what do we get? And we see ickiness. These weren't as close to whole numbers as we would like. So experimentally then, as the book explains, it depends on where you think errors could have come from. If you think everything is going well and these numbers are consistent with your experimental equipment, in other words, you can be this precise with your numbers, then the trick here is to look and say, okay, this is close to a whole number if I multiply it by 2. Same with this guy. So this is essentially 3.5 and 3.5. Multiply it by 2. This is 1, so oxygen would become 2 moles. I'm sorry, yes, 2 moles, because it was 1 mole here. This would become 7 moles, as with this. So this is a good learning lesson. Don't know if you noticed that that number magically changed, and it did indeed. And it did because I made an error in button pushing, in part because when I got down to here and said that these two things are 7 and 7, I knew that answer to be wrong. And look back up here and I had 5.6 for 5 divided by 1.008. So yeah, I did not pay attention. I didn't yield my own advice on look at it and double check mentally what you expect to get instead of just button pushing and running with it. So with that, let's change this to 4.968, or 4.96 divided by the 1.639. 4.96 divided by 1.639 is 3.02. That makes sense. 3.026. So the same rule applies though. So this is close enough to 3 that I'd be happy with that. This obviously is 1 because we divided it by itself, but we still have this ickiness. So because this is kind of hovering the line, you do want to go with the multiplying by 2 in order to make it a nice whole number, or relatively close. And so this still is indeed 7, but the difference is this is now 6, as it should be. Good. So that was a nice little lesson in making sure that you pay attention to what you get out being the same as what you think it should be. So then this equation, we would say for benzoic, would be C7H6O2 for the empirical formula. We have not determined if that is the molecular formula.